Since the antiquity, people hypothesized that matter was composed of small particles, atoms. But in more recent times, scientists proved the existence of even smaller particles. In the 19th century, the electron and then the proton were discovered. In the 20th century, it was the time of the neutron. With the development of quantum mechanics, more pieces were added to the puzzle, and scientists converged towards the formulation of the Standard Model, which aims to classify all currently known particles. Following the developments of quantum mechanics, starting from the 1930s onward, it was commonly recognized that there are four forces that govern the universe. Gravity, the oldest known one, acting through the mass of a body, explained by Newton's theory of gravity first, and then by Einstein's general relativity. The electromagnetic force, discovered in the 19th century and leading to the exploitation of electricity, acting on the electric charge of a particle. The weak interaction, theorized in the 20th century and responsible for radioactive decay, acting on a different type of charge called flavor. The strong force, also theorized in the 20th century and acting inside the nuclei of atoms, acting on another type of charge called color. The weak and strong forces act on very small distances, subatomic and nuclear ones, and for this reason, they're not commonly experienced in the macroscopic world. The Standard Model of particles involves three of these sources, all but gravity, and classifies all simple particles, that is, indivisible particles, based on their interaction with each force. First of all, particles are divided into fermions and bosons, depending on their spin, the angular momentum carried by the particle due to the rotation on its own axis. Fermions have half-integer values of the spin unit, while bosons have integer values. Fermions are the particles that compose matter, while bosons are the vectors of the fundamental forces. Among fermions, we have the elementary particles that are the basis of everything, quarks and leptons. They are currently believed to be the simplest particles, which cannot be divided into smaller ones. Among leptons, we find the electron, the muon, and the tauon. Each of them has electric charge -1 and the leptonic number +1. They don't have color charge, and therefore they're not subjected to the strong force. Each lepton has an antiparticle, or antilepton, characterized by opposite electric charge and leptonic number. The antielectron is also called positron. When particle and antiparticle collide, they annihilate and produce energy. Leptons are subjected to the weak force according to three flavors: electronic, muonic, and tauonic flavors. Only particles with the same flavor can interact with each other. To each lepton is associated a neutrino, having neutral electric charge, the same type of flavor, almost null mass, and the same leptonic number. Within an interaction, charge, flavor, and leptonic number are conserved. Quarks are the elementary particles that make up all the more complex particles. They are the only elementary particles subjected to all four fundamental forces. Therefore, they have electric charge equal to a fraction of the charge of the electron. Color charge, conventionally named red, green, or blue. And flavor. The quark flavors are 6, up and down, charm and strange, top and bottom. As for leptons, quarks have their antiparticles, called antiquarks. Quarks are held together by a strong force to create more complex particles, called hadrons. Among hadrons, we find mesons, particles composed by an equal number of quarks and antiquarks of different flavor. Mesons can be electrically charged or neutral, and they have an integer spin. They are therefore bosons. An example is the pion. Mesons are commonly found in cosmic rays. Baryons are composed of an odd number of quarks. Among them, we find the proton, composed by 2 up quarks and a down one, and the neutron, composed by 2 down quarks and an up one. Their antiparticles are composed by their respective antiquarks. Baryons can be electrically charged, like the proton with charge +1, or neutral. A proton can transform into a neutron when an up quark transforms into a down one, with the intervention of the weak force. Protons and neutrons are held together by a strong force to create the nucleus of an atom. Baryons have half-integer spin and are therefore fermions. At the beginning, we have mentioned elementary bosons, elementary particles with an integer spin value. In the Standard Model, elementary bosons with spin 1 are the vectors of the electromagnetic, the weak, and the strong forces. For the electromagnetic force, we have the photon, massless particle with neutral electric charge, a quantum of light. For the weak force, we have the Z, W+, and W- particles, respectively neutral, positively, and negatively charged. For the strong force, the vector particle is called gluon. The only elementary boson of spin 0 is the Higgs boson. Interactions with this particle allow the vector particles of the weak force to acquire mass, and the Higgs boson can transfer energy to massless fermions, quarks and leptons, providing them with their mass. Within the Standard Model, gravity remains unaccounted.